everybody. Welcome to our third lecture on X-ray diffraction. I'm going to get my laser pointer going so I can kind of talk about the first slide of the lecture for today. And a lot of times I talk about this class being about being able to differentiate between black and white or contrast to analyze the data output by our characterization instruments. X-ray diffraction is pretty much the way we use it these days, a flavor of spectroscopy. And so we look at lines on a screen. And here's an example of some recent work that we're actually doing in the lab. And this is actually a polymer spectra. And polymeric materials do indeed exhibit a flavor of crystallinity. And we're going to be talking about crystallinity and crystal structure and how that interacts with X-ray diffraction for this lecture. So I thought spectra like this was quite appropriate to start the lecture off. And so we have two spectras here. So we have this blue line and we have this black line, and there are two different conditions. This blue line is amorphous, and when you see a big hump like this on an X-ray diffraction spectra, that means there's some amorphicity if it's very, very wide. When you see these peaks here, and there's actually quite a few. I don't want to get too far into this research because it'll kind of distract from what I'm trying to get to. But we were actually surprised to see this many reflections. And so if you see peaks like this, these count as reflections, and these reflections correspond with the dots that you saw in the other diffraction pattern at the beginning of lecture 2. So for a visible diffraction pattern, we see spots. For a diffraction spectra, those spots are replaced by peaks. Okay, and then you can actually calculate the d-spacing of these peaks as well. So this black line exhibits a level of crystallinity. So we've processed the material in this black line differently, so we imparted a degree of crystallinity to our polymeric specimen, and we can interpret that by X-ray diffractometry, by looking at these peaks, and where they lie kind of tells us some stuff as well. And we'll get further and further into this in the next two lectures. But first we need to talk about a little bit more about crystallinity. And in this case, not talking about crystallinity in polymers, but talking about crystallinity in the materials that we're pretty much more familiar with as metallurgists, metals. Crystallinity, the way society and the way we as humans have tried to characterize matter has always had to do with some sort of shape. And it was these so-called platonic solids that were first kind of had this shape kind of theme being applied to characterize the stuff around us, the substances around us, if you will. And fire was represented by the tetrahedron, air was represented by the octahedron, something that was solid was represented as a cube, which is actually kind of interesting if you think of metals. And most metals we deal with from an engineering perspective, at least in the raw elemental stage, or some sort of cubic structure with the exception of titanium. Liquid icosahedron, and the surrounding cosmos was this pentagonal dodecahedron, and these again are the so-called platonic solids. It's kind of interesting to think about things. So if you have a cube of salt and sodium chloride, if you will, the salt will tend to cleave, and it'll cleave with planes that are coincident with 1, 1, 1, and that's all this little cubic structure trying to lower its surface energy. Kind of a little segue, but it popped in my head when I was looking at this cube for some reason. But bear that in mind. So the way society, at least Western cultures, have tried to characterize the world around us has been by associating some sort of shape with each of the elements. So we want to think about what is a crystal, and kind of have this bullet down here. So a crystal consists of atoms arranged in patterns which repeat in 3 dimensions. So kind of a repeating structure is a key characteristic on whether or not a substance is crystalline or not. And if we look at this unit cell, I think this is face-centered cubic. and I did my best to draw it as face-centered cubic, painstakingly drew it in PowerPoint, had to Google how to make a sphere in PowerPoint, so this isn't a circle, it's actually a sphere, even though I probably could have achieved the same result just by drawing circles. But anyway, I wanted to throw that out there. So we have a repeat structure. So we have our base unit cell, and then it starts repeating in 3 dimensions. And hopefully you can see that as I animate. So I'll go back and forth to hopefully make it more apparent. If you're staring at the screen, we'll have another unit cell appear to the left of our original unit cell, and then we have another one appear to the front of our original unit cell, and one above our original unit cell. So now we've kind of repeated in 3 dimensions. I probably should have had one go below to be truly 3-dimensional, and probably one behind it and to the other side. But hopefully you all get the picture. A crystal consists of atoms arranged in patterns. These patterns repeat in 3 dimensions. Unit cell. How do we characterize a crystal? So hopefully this is review for some of you, or all of you actually. And we typically characterize a crystal with 3 sides, and we usually don't denote these as A, B, and C, and we denote the angles that characterize the angles between our sides as beta, or alpha, beta, and gamma. So 3 sides A, B, C, 3 angles alpha, beta, gamma. How these relate to one another gives us the Bravais lattice, and it's defining the building blocks of pretty much all materials, at least all crystalline materials. Don't forget this. I'm pretty sure you guys have had this. You all have had this since day 1 of Intro to Materials. In the event that you haven't, there's 7 lattice systems, 14 Bravais lattice structures. It's good to know them. It's also good to be aware of the different designations that are used. And I actually think it's between British and US, kind of like aluminum and aluminium. Anyway, beware of the different designations. I'll kind of show that right now. Here is the designation of the 14 Bravais lattice structures derived from 7 crystal systems, and we want to show this here that rhombohedral is what our book denotes this crystal system as. So rhombohedral is A equals B equals C. I have to get a little closer to look. I should have this memorized. Alpha equals beta equals gamma, but none of them are equal to 90 degrees. Okay, so that's rhombohedral. On other Bravais lattice structures, rhombohedral becomes replaced with trigonal, and it's a little bit easy to read. So anywho, 7 crystal systems, what are they? There's triclinic, monoclinic, so you have simple, and base-centered monoclinic. So here's 1, 2, simple orthorhombic, base-centered, body-centered, face-centered. Oops. Sorry, base-centered, body-centered, face-centered, so that's orthorhombic. So we have 1, 2, 3, so triclinic, monoclinic, orthorhombic, that's 3. We have tetragonal, that's 4, so simple and body-centered tetragonal. 5 is trigonal, sometimes called rhombohedral. 6 is hexagonal, which titanium always pops in my mind. I know there's other materials that are hexagonal, but titanium's my favorite, if you will. And then cubic, which is, so hexagonal 6, and cubic, the cubic system is 7. So 7 Bravais lattices. When you break them down, you have different flavors of some, not all. So there's only 1 flavor of triclinic. There are 2 flavors of monoclinic. There's orthorhombic. There are base-centered, body-centered, face-centered, and simple. So there's 4 flavors of orthorhombic. For tetragonal, there's 2, so simple and body-centered tetragonal. Trigonal / rhombohedral, there's only 1, and there's only 1 hexagonal. Some people claim or assert that this crystal structure trigonal is actually a subset of hexagonal. I saw it once in a figure, and I can't visualize it, to be honest with you, but some people probably can because they're all smarter than me. Anyway, simple cubic, body-centered cubic, face-centered cubic. 3 flavors of the cubic system. Why do they do this? Well, if you go back to 101 materials engineering, you have 2 atoms coming together. there's attractive and repulsive forces. You reach an equilibrium point for these atoms, and basically these are the equilibrium points for a grouping of atoms in this crystal structure. So these atoms have all reached their specific equilibrium points. These equilibrium points will differ for various materials. Okay, so the fact that each material will have its own equilibrium point, which will give us a specific lattice parameter slash crystal structure, okay, means that we can actually use X-ray diffraction to identify what the materials actually are. Okay, so these equilibrium points from a simple model of atom A meeting up with atom B of the same substance, finding this equilibrium point on a greater scale gives us one of these unit cells, and on an even greater scale gives us a repeating unit structure, or crystal structure, excuse me, allows us to analyze this material via X-ray diffraction. Very interesting stuff. Structure property relationships, kind of wanted to throw this in here. So this is 6,4 titanium, one of my favorite alloys. The black phase, so again using contrast to interpret our results, if you will. This black phase is beta, which is body-centered cubic. White phase is alpha, which is hexagonal close-packed. Alpha is the primary phase. It's stable at room temperatures. If you see beta in a titanium microstructure, that means something was added to stabilize it, and so probably vanadium. You don't want the beta to take over, so you have to put in a little aluminum to stabilize the alpha. That's why you have 6,4 titanium. Alpha is generally the softer phase, and black beta is the beta is the harder phase. So different structure property. This is a more densified version of titanium, more densified flavor, which is why it's harder. Yeah. Okay, D-spacing. So we have the 100 plane. Let me get my laser pointer. And we have this lattice parameter. So we refer to lattice parameter as A, and you all should have seen this at some point in time. So the lattice parameter is the distance between one atom and another atom in a crystal structure, or in the same unit cell, if you will. In this case, the D-spacing is the same as A. Okay, so that's not always the case. So from one 100 plane to the next 100 plane, your D equals to A. Pretty simple. It's a cubic structure, and we see this kind of repeat pattern here. Not always the same. The punchline of this slide is to let us know that D spacing is the distance from one plane to the next same plane. Okay, so the distance from one 100 plane to the next 100 plane in the neighboring unit cell is D. So that's what D spacing means. Not always the case where D will equal to A. We generally use this equation to calculate the D spacing for a cubic cell anyway. So D equals A pretty much over your Miller indices. And so here D equals the square root of 1. And so if we had our lattice parameter for our material, we could calculate what the D spacing was. I don't know if we really have to go through this calculation, but it's always good just for exercise points of view. If you had 110, it would be a little bit more complicated. So it would be A over the square root of 2. If you had 111 and you wanted to calculate the D spacing of 111, it would be A over the square root of 3. So very simple for cubic structures. If you look at the appendix, so this is the appendix from Brandon and Kaplan. This is, I always hate it when they inverse this stuff, but hey, this is what we get. We can rearrange this if we needed to. If you look here, I rearranged D equals A over the square root of 8 squared plus K squared plus L squared. That came from this somewhat more complicated flavor of the same equation. But you can see it differs for different crystal structures. Okay, so cubic, simplest, tetragonal, a little bit more complex, Orthorhombic, a little bit more complex. Hexagonal, it's kind of complex. Rhombohedral scares me. And monoclinic's a little bit more complex as well. So you kind of have to know the lattice parameters, and in some cases you have to know the angles between planes. Okay, so for monoclinic you'd have to know beta, and for rhombohedral you'd have to know your alpha angle. Triclinic is spooky. This is crazy, and I don't think I'd ever have anyone work this out. It's kind of crazy. Maybe I should. I don't know. So let's kind of work out a quick problem based on the lattice parameter of iron. The d-spacing of, or the lattice parameter of iron is 2.87 angstroms. The d-spacing of 100 is 2.87 angstroms. Okay, it's cubic, so we know. We saw in the representation what 100 is. What's the d-spacing of 200? And we kind of insert this extra half plane. So the d-spacing of 200 is if you can work it out. So there's two ways you can do it. You can work it out. So you can say d equals 2.87 over the square root of 2 squared. Or you can visualize it. Okay, so the d-spacing is 2.87. So the d-spacing of 100 is 2.87. The d-spacing of 200 is half of 2.87. Okay, because it's the half space. So that's one way to think about it. And we can work it out the long way right now. So dealing with d-spacing and lattice parameter and that type of relationship, we have our series of equations, and they get more complex for anything that isn't cubic. But in this case, we're dealing with iron, which is BCC, so it falls in the cubic system, so we can use the equations for a cubic crystal structure. Lattice parameter, let me try to make my pen a little thinner. Lattice parameter of iron, A is 2.87 angstroms. And so we know the d-spacing of 100 is 2.87. We visualized it on the previous slide. We can kind of guess what the d-spacing of 200 is, but let's just work through it anyway. So what's d? D of 200. D of, and so this is the family of planes. We could also do 020 or 002. It'd work out the same mathematically. D equals A over the square root of 2 squared plus 0 squared plus 0 squared. And hopefully you can read the writing. So D now equals, I should have put 2.87 in the first place, over the square root of 4. And so D equals 2.87 over 2. So this is supposed to be a 4. You didn't see it well because of my poor writing. And so 2.87 divided by 2, again, this is pretty much the half spacing of 100. So it kind of makes sense that D would be 2.87 divided by 2, which is 1.44 thereabouts. D equals 1.435 angstroms. If we care about significant figures, we can round up. 1.4 angstroms. All right, so we know that for a crystal structure for a metal like iron, which would be BCC, and for copper, which would be FCC, that we have a crystal structure, repeating structure. And so Laue, the scientist Laue, was one of the first people to actually start messing around with X-rays. And he came up with the so-called Laue equations. And these equations are based on a path difference. And let me get my laser pointer. And so if you look, let's just say these are incoming X-rays, and here are a row of atoms. There's going to be a path difference between the X-rays hitting this row of atoms and after they've hit this row of atoms, okay? And so Laue realized that there was a photon / material interaction with rows of atoms or with crystalline materials. And you have to remember, back when Laue was doing this stuff, there wasn't this fundamental knowledge of how material was arranged, of how atoms were arranged. This kind of atomic structure was still kind of being theorized, and they didn't really have the tools to analyze materials like we do now. So it wasn't factual to them that metals were arranged in a repeating structure, but his early experiments were shining light on the fact that materials were arranged within a repeating structure. So Laue came up with these equations. He realized that there's a path difference between the incoming and exiting X-rays. Okay, so he was doing this work with X-rays and different materials or crystals that he found out and about, I guess, and kind of created this kind of so-called triangle math. And you kind of see this repeating structure of our repeating theme of triangles. And there's a path difference between this X and Y. Okay, so delta, and you have to realize that the path difference is going to be an integer of the wavelength of your X-rays. Okay, and here for A, he denoted the integer of H, and it has to be 1, 2, or 3. Okay, so it can't be 1.5 or anything like that. So H is going to be 1, 2, or 3. Okay, and we'll just assume 1 for simplicity. So there's a path difference delta, and it's y minus x. And so why is it y minus x? Well, y, as he's depicted it here, is greater than x. Okay, so it's going to take a longer distance to get from point A to point B. I don't know if my explanation made that great a sense, but based on this triangle math, the line x made by x is going to be less than the line made by y. Okay, so that's why delta is y minus x. Delta also equals an integer times the wavelength of light. Based on the geometry we have here, we have different angles alpha. Okay, so the line x makes an angle alpha naught, and the line y makes the angle alpha. And so these atoms are separated by the lattice parameter A. So delta equals A cosine alpha minus cosine alpha naught. Delta also equals H lambda. Okay, so if you remember, this is only one side. So this is the side A. And again, path difference, I saved the animation because it was kind of obscuring what I was trying to point out. But there's a path difference, y minus x. If you take this same scenario for the 3 sides and the 3 angles that make up a crystal structure, you end up with delta equals H lambda, delta equals K lambda for side B, and delta equals L lambda for side C. So A corresponds with H, B corresponds with K, C corresponds with L. These are the so-called Laue equations. They're describing the path difference between your incident and your scattered beam. Laue is doing this awesome stuff, realizing that the beam of light, if you will, the ray of X-rays, if you will, ray of Roentgen radiation, was being manipulated by a repeating structure in the material he was examining, gave us these Laue equations. The key thing that we still use today are HKL. So it's where HKL notation comes from. So it comes from Laue. Always kind of pay homage to some of the history of the stuff we work with. The origin of the crystallographic equations developed by early crystallographers. So interplanar spacing is a function of Miller indices. So people started working with Laue equations, started working out math to kind of figure out this stuff, and it's actually dot and cross products that make these equations. So d equals a over h squared plus k squared plus l squared is what we live by for cubic systems. There's different notations here, and so I'll just kind of quickly go through here. I think I messed up. I shouldn't have had d equals hk squared, hk plus k squared plus l squared. But anyway, look at the appendices, okay? But these are the equations that people were dealing with, and these are kind of vector notations, and they were using dot product and cross product. And we'll see kind of these artifacts of the math behind some of the stuff we deal with in the actual practical equations that we use. So this would be a practical equation, d equals a over h square root of h squared plus k squared plus l squared. All came from dot product math. The notation came from Laue. And anyway, just kind of paying homage. If you look at diffraction now, okay, so Laue equation, very complex, okay? You have three equations to try to piecewise everything together. Bragg's law is far more elegant. We'll talk a little bit more about that today. You look here, you have the beam diffracting on this row of atoms versus the beam diffracting on this row of atoms. Okay, so the crystallographic planes are essentially a mirror. And if you're at the right so-called Bragg condition, you will achieve diffraction. Okay, so if this incident beam is the correct angle theta, you will achieve diffraction, and this angle is a so-called Bragg angle. And we're going to talk a bit more about Bragg's law. So Bragg's law is n lambda equals 2d sine theta. D is the d spacing, so hopefully the slides before this clued you in to what d spacing is if you didn't already know. Sine theta is the angle of the incoming X-rays, and lambda is the wavelength. N refers to order of diffraction, and for practical purposes we usually say n equals 1 when we work some of this stuff out. And this is supposed to be theta, so I had a boo-boo on my PowerPointing. So these guys won the Nobel Prize for Bragg's law, and there's kind of the legend that says the father, Sir William Henry Bragg, is actually the person that did all the work, but William Lawrence Bragg actually published it, and I think made his dad quite angry. But in the end, they were both awarded the Nobel Prize in physics for developing Bragg's law in 1950. So they earned the prize in 1915. I'm not quite sure when they actually came up with Bragg's law. N lambda equals 2d sine theta. One thing to think about X-ray diffraction, and we're going to see some of this stuff again when we talk about electron diffraction, pretty much the same thing, both kind of relying on the wave-particle duality of the photon and electron. They're an elastic process, so no energy is lost. The wavelength is unchanged. The crystal lattice is regular and repeating structure, and so the interaction of X-rays and electrons with this structure creates diffraction patterns, and we've seen that at the beginning of lecture 2 with those spots. All right, so derivations of the world-famous Bragg's law. Again, let me get my laser pointer going. Again, the n refers to order of diffraction. It has to be some integer of lambda. And if you go and Google Bragg's law, as maybe it would be a good idea to, and I did, and that's where I got this picture from. I happened to find it from this web page. I could probably have drawn it myself, but it's all over the place. So this is probably the most common depiction of how to derive Bragg's law. It's the most simple derivation of Bragg's law, and I don't like it, and I'll tell you why. But I altered this picture by adding point X and point Y. And the reason I did that is because you have this X-ray beam, and it bounces off of this plane of atoms. And you have, and so this is AC. And then you have another beam of X-rays, A prime to C prime, that's bouncing off the next row of atoms. And you have a path difference now, and the key to Bragg's law, which was also the key to Laue equations, is some sort of path difference. Okay, and that's kind of the principle of diffraction, I guess, if you want to think of it that way. And that path difference is given by the summation of line xb prime and line b prime y. And you can then use this kind of right triangle geometry. And well, so first, I kind of got ahead of myself, sorry. First, you have to realize that xb prime is equal to b prime y. Now you can use your right triangle trigonometry or geometry and realize that sine theta equals xb prime over d, because this length is given to us by our d spacing d, the inner atomic distance there. And so we could rearrange this equation and say xb prime equals d sine theta. So we're starting to see some similarities now with Bragg's law. And we can do some substitution with our first equation describing path difference and our other equation that tells us that xb prime equals b prime y, and say that n lambda now equals d sine theta plus d sine theta, because both of these line segments are signified by d sine theta. So now we have our proper Bragg's law, n lambda equals 2d sine theta. And this is fine and dandy, but I really hate this representation. And I hate this representation, I've always hated it, because you have this extra line segment here that just kind of is ignored. And the reason why they ignore it is because I call this the so-called geometric, or the D-row-called geometric derivation of Bragg's law. And because the other flavors of Bragg's law derivations, they're very similar, and I discussed it before. They're very similar to the figure in the book that shows the rows of atoms acting like a mirror. And here's one such derivation, and this picture looks very similar to the figure in the book. And you see it's a lot more complex. And so we have these three triangles that we've kind of derived from this diagram. So this is similar to the figure in the book, where you have the mirror effect of the atoms bouncing here, and then you have another mirror effect of the atom bouncing off of B here. And so now you have this path difference, which could really be thought of as these two segments here, okay, A to B and B to C. And you have to solve for these three triangles, and I'll let you pause it and stare at it if you're interested, and then use some trig identities to get through some of this stuff, namely 1 minus cosine squared theta being the trig identity, and 1 minus cosine squared theta equals sine squared theta. So that's a critical trig identity. Anyway, you can then get Bragg's law that way. This is the way I learned it. I mentioned I learned it, I think I did mention it earlier, with laser scatterometry. Again, another trig identity. It's the same one, but a different derivation. It's my humble belief that people accept this kind of, I call it the baby way to derive Bragg's law, because they want to be able to do it the most simple way possible, so they draw a convention that's patently incorrect. And for me, this is the more correct way, one of these two variations, to derive Bragg's law. We'll have this other derivation later. This is in terms of k vectors, so we're talking about k space. And maybe I should talk about it here because X-ray diffraction can be thought of in terms of K-space. You then get another flavor of Bragg's law, and this is kind of a two-dimensional lattice. Don't stare at this too much because I'm going to save this flavor of Bragg's law for electron diffraction. All right, so Laue, this is kind of a simple depiction of a Laue diffractometer. And so we have our X-ray source somewhere over here. The X-ray passes through the crystal and we create this crystal pattern. So we have a dot here and a dot here. We have the center spot. So we're going to have the first order reflection given to us by radius 1 and the second order deflection given to us by radius 2. The d-spacing of the first order is always going to be greater than the second order, and so forth. So as the rings go out, your d-spacing is actually decreasing. So don't forget that. We'll kind of bear that more in mind when we deal with electron diffraction. If you take this to angle theta, and you realize that this is a right angle here, because you're hopefully, I don't know if you can tell by this depiction, but it's like you're projecting it on a wall or something that makes a right angle with the distance d. So d is the distance between your specimen and the recording plane, and r is the radius to the first single, or r1 is the radius to the first circle, and r2 is the radius to the second circle. So you can calculate, actually you can calculate theta, okay? And here r actually equals to the d spacing, and or it's analogous to the d spacing, okay? To get the actual d spacing or lattice parameter, you could then plug that into Bragg's law. So you can solve for theta based on your measurements, plug that theta in the Bragg's law. So Laue diffraction, you can use it to create simple X-ray diffractometers, pinhole and photographic film. The d-space, the actual d-spacing can be calculated by inserting the value for theta into Bragg's law. And it's also used in single crystal diffractometers, as I've mentioned before. Let's work out a Bragg's law example. And maybe I shouldn't be drawing it this way, but let's just go with it. So let's just say this is the 111 plane. I tried to make it angled so you see it's 111 plane. Lambda equals 1.54 angstroms or angstroms. Copper K alpha. The silver, so this is silver, is the lattice constant. So we're examining silver, and the lattice constant A equals 4.09 angstroms. And so we want to know, does this example satisfy Bragg's law? So let's go ahead and work through this right quick. When I work through it, I think it'll be a little bit less confusing than I've depicted it here. All right, so we have our Bragg's law example. This is 111. I've kind of drawn it with this little angle to kind of show you that it's 111, and I'm almost scolding myself for the way I've drawn this. So this would also be theta. This would also be theta. If you look at the way I drew it, it makes you think that it's always 45 or always 90 degrees. That's not necessarily the case. It's just kind of the way I drew it. Collectively, this is 2 theta. And so kind of foreshadowing the X-ray diffractometry, the x-axis is always given in terms of 2 theta. And that's because the detector is always referenced with respect to the source. And so this is why it's 2 theta on an X-ray diffractometer. But that's kind of a segue moving ahead. We want to know if this example, if 15 degrees is indeed the Bragg angle. And so we want to kind of figure it out. So we're using lambda equals 1.54. And so lambda equals 2d sine theta. We're assuming n equals 1. We wouldn't be scolded for doing so because 111 would be a first order reflection as well. And our lattice constant A is 4.09 angstroms. And I'm going to keep that level of significant figures because you have to be pretty precise with X-ray diffractometry. So A equals 4.09, and then I'm going to leave that O off. So 4.09 angstroms. And So we want to figure out D, okay, because we're wanting to find if theta is correct, and or if theta would be a Bragg angle. And so we already know lambda is 1.54. We can figure out D from A because we know silver is cubic, so it's FCC. And so we're going to solve for theta in this case. And so let's first figure out D. So D equals 4.09. Sorry, units are going to come from our lattice parameter angstroms over the square root of 1 squared plus 1 squared plus 1 squared. And so D equals 4.09 angstroms over the square root of 3. Let me pull up my fancy calculator. All right, so 4.09 divided by the square root of 3 is 2.361. And I will write it out. All right, so we have D, we have lambda, and we have to solve for theta. And so sine theta equals lambda over 2d. Theta equals, oops, sine negative 1. I tried to draw it ahead of myself, over lambda, over, 2 times 2.361. And so 1.54, sorry. I think I'm overcomplicating this. Over 2 times 2.361. Sorry about this, y'all. Okay, 1.54 divided by all right, so I got 19.03 for theta. So this does not solve Bragg's law. No, it does not. It does not solve Bragg's law. So kind of thinking ahead, what angle would solve Bragg's law? And we kind of already did it. What angle would solve for Bragg's law? The angle we actually got. So 19.03 would actually solve for Bragg's law. Come on now. There you go, 1903. So if someone asked you, well, what angle would solve for Bragg's law? 1903 would solve it. So we worked through this one, and we found that it really didn't satisfy Bragg's law. We then asked the question, well, what angle would satisfy Bragg's law? And well, the answer, when we proved that it didn't satisfy Bragg's law, was roughly 19 degrees. The whole point of this exercise, and you could also work it out the other way and solve using theta and try to figure out what last parameter you get or something. You could work it out the other way. But the thing you want to walk away from this little exercise is, in general, it's hard to satisfy Bragg's law. And that is what makes X-ray diffraction such a powerful tool. It's actually hard to satisfy Bragg's law, so you can actually get a distinct identifier of your materials, basically. Kind of pose this question too, kind of rehashing what we said before, and I actually hate this diagram because it makes you think that it's always a 90-degree angle, but it's really not. The XRD spectra is always reported in terms of 2 theta, and if you go back to the first slide, you'll see, yeah, it was reported the x-axis was 2 theta. Why, you may ask? Well, the detector is always referenced with respect to the source, And so if you draw a line continuing from the sample, from the source, and you actually get 2 theta from that, right? So theta, theta, 2 theta, always reported in terms of, or with respect to the source. That's why. Another question, I'll just kind of throw this in now. The limit to resolvable d-spacing. So there are some people that say that if you have a d-spacing that's less than lambda, you can never diffract it. Well, according to kind of rule of thumb theory, half the wavelength is actually the resolvable d-spacing. And that's a rule of thumb, okay? Always remember it's a rule of thumb because you're ignoring part of the equation. If you say lambda over 2 equals d, you're removing part of the equation. So it's a rule of thumb. But we'll see another representation of this later. And so this is a shout out to VeggieTales, a good place to stop and think about what we have learned today. And we'll pick up some more meatiness, if you will, of X-ray diffractometry in the next lecture. Thank you very much for your time.
Oh my.
It's the end of the lecture. If you have any questions, you can email me at drobertson@utep.edu.